Hey everybody. So this lecture is a little different from some of the rest of them. We're going to be talking about black holes, time travel, warp drive, all that cool stuff. Most of this stuff you're not going to need for later on in the semester. So when you pull your class notes out, the only thing that you need to learn is what's on your class notes. So that's actually a fairly small percentage of everything that's in the lecture. So for the most part, I want you to just kind of sit back and enjoy and follow along what's going on and let it just kind of blow your mind a little bit for that. All right, let's get started. Okay, so as I said, we're going to talk about black holes. Now, we briefly mentioned them last time when we were talking about stellar evolution, how stars are born, how stars die. And you know that black holes only form from the very largest stars. So let's get into the details about how they're formed. So as I said, have your class notes out and remember that the only things you're going to need to know for this section is just what's on your class notes. Everything else that we're talking about, all the bizarre time travel and warp drive stuff, that's really just for fun. So pause the video until you've got that out and you're ready to go. All right, so we talked about how a high mass star dies in a supernova. When it dies in a supernova, what's left over is that neutron star. And so normally that neutron star is supported by neutron degeneracy. And remember, degeneracy is when those marbles, either electrons or in this case neutrons, are just kind of stacked up on each other. Normally they're free to move, they're going to vibrate, they're going to do all their things. But as they get compressed, there's a limit to how close they can get together. Well, if I have more than 3 solar masses of non-fusing material, remember if it's fusing, then it's going to be providing support outward. So if it's just collapsing, if I've got more than 3 solar masses of material in one place, then even neutron degeneracy can't stop the collapse. Effectively, the marbles crack. And so then at that point, they get crushed, and there is nothing that can stop the collapse. There's no force in nature that can stop that. And so it collapses down to size 0. Not very, very small, 0. Now, one side note for those who have looked into this before, we're not going to be dealing with quantum mechanics in this. General relativity, which describes black holes, is what we call a classical theory. It doesn't use quantum mechanics. So everything that I'm giving you is based under general relativity. Okay? All right, so it collapses down to size 0. And it's important that you understand that all of the mass is still there. It's just in that one tiny little speck that we call the singularity. Now, the region from which light can't escape is somewhat larger. So let's look at that. So the escape speed inside this part here is actually greater than the speed of light. So any light that tried to leave from near that singularity, that thing that's in the very center, it gets pulled back down, and so it can't escape. So what you're looking at here, what most people think about as being the black hole, is actually called the Schwarzschild radius, or more commonly it's called the event horizon. And that's because anything that happens inside this region can't escape. We can't see the light from it, and so we can't get any information from it. It all just is going to get pulled back down onto the singularity in the very center here. So this event horizon is not anything physical. When you cross that event horizon, you can't tell anything has changed, because all that is just the limit from which light can't escape. That's it. The size of that event horizon is actually very easy to calculate. You just take the mass of the singularity down here in the middle, take the mass of that singularity in solar masses and just multiply by 3. And that's going to be the size of this event horizon from here to here in kilometers from that. So also notice, as you can see in this picture, that the event horizon is really a sphere. It's not a flat disk like it's shown sometimes. And if you think about it, that's because it's not anything real. If I'm going in this direction, then light can't escape. If I'm going in this direction, light can't escape, and so on and so on. So all around that singularity is the range at which light can escape. Well, as I get farther and farther away, eventually I'll get past this boundary here, and now light can just barely escape. And so that's why it looks dark. That's why nothing that comes into here we can still see. So the very first black hole discovered was Cygnus X1. You may have heard of that. And this is it right there, that little X-ray source. And it's actually a binary system. The primary star is actually a Class B supergiant. So this thing's so bright that you would be able to see it with your naked eye, except for the fact that there's a dust cloud between us and that supergiant there. So you can't actually see it without a telescope. It's ninth magnitude. Sixth is the faintest magnitude that you can see without a telescope. And we'll get into magnitudes later on. One thing, Eta Cygni, right here, this is in the constellation Cygnus, obviously. Eta Cygni is actually a fairly bright star. You can just get outside of Phoenix and you'll be able to see it without any trouble at all. So that shows you about where, once you find Eta Cygni, you can find where Cygnus X1, the black hole, should be. So when we were looking at this, we had this X-ray source that just seemed to be coming out of nowhere. There was no star there, there was no object there, nothing that we could see. It wasn't emitting any visible light. And what we figured out is that mass is falling from the B star here down onto the black hole. And once it crosses that event horizon, of course, now that matter is going to fall down on the singularity. It's going to get crushed down, back down to size 0, and the mass of the singularity, the mass of the black hole, gets bigger and bigger and bigger. So, but as this material falls down, it's giving up gravitational potential energy. And if you think about it, if I have my pen here, and I've picked it up off the ground, I've stored some energy in here. When I let go of that pen, it falls. It converts that gravitational potential energy into motion, into kinetic energy. It also converts it into heat, into thermal energy as this thing falls. Well, there's so much potential energy being lost. This thing it's like it's falling from an incredibly great height and then falling at an incredibly great speed, that it turns that gravitational potential energy into just radiated energy. And then it's going to be mostly X-rays from there. So this is what a black hole system looks like. Now, if the black hole doesn't have a companion star, we've really got no way of detecting it. There's some tricky things we can do with microlensing that we'll talk about. But for the most part, when we're looking at black holes, we're looking at these companion stars, and so we can see the energy as that stuff falls into the black hole. Now, in addition to regular black holes, we're going to talk about supermassive black holes, and we'll get into this a little more detail when we talk about the Milky Way galaxy. But it seems that almost all galaxies have a supermassive black hole in the middle, and by supermassive, we mean millions of solar masses. So let's suppose that I have a star that is 1 million solar masses, a black hole that is 1 million solar masses right here in the center of this galaxy. What is going to be the size of the event horizon? Pause it if you need to go back or look at your notes, think about it. Pause the video, figure that out. Well, it's real simple. You just multiply by 3. And so the size of the event horizon, the region from which light can escape, is about 3 million kilometers. That's a lot. Now, the reason why you can't get too close to a regular black hole, let's say that's a stellar-sized black hole. Well, that thing's only going to be, maybe a few miles across, something like that. Even here on Earth, if you jump off a table, your feet are closer to the Earth than your head. And so your feet are actually feeling a stronger gravitational pull. Your feet are actually falling just a little bit faster than your head. You're being stretched just a little bit. Your muscles can handle that without any problem at all. However, if you're falling towards a black hole, now your feet are falling much faster than your head because there's a big gravity difference between those two. And so you start getting stretched thinner and thinner and thinner. And that's actually what's going to kill you. You're going to be dead long before you get to the event horizon because you've been pulled into this long piece of spaghetti, and then your atoms will be stretched out and all that. It's a pretty painful way to die if you think about it. So, but however, with a supermassive black hole, you are just a tiny little dot compared to 3 million kilometers. And so the difference in gravity from one side of that dot to the other side of that dot is not very big. So this would be the type of black hole that you could conceivably explore and actually survive. You could cross the event horizon and see what's going on inside. Now, you're not coming back, but at least it's not going to rip you into an infinitely long string of spaghetti as you're falling down towards it. So the supermassive black hole was verified by looking at the orbits of stars. These are the stars in the very center of the Milky Way. So these bright spots that you see. This particular picture was taken in infrared. We can't see them invisible because happens to be a big dust cloud between us and the center of the galaxy. So unfortunately, from our perspective, that's blocking all the light. Somebody else on another part of the galaxy could possibly see all the way in. So we look at these stars in infrared, and these are the two closest stars here. This is star SO102, this is star SO2, and you see that they're orbiting something that's not putting out any light right here, right in the overlap between those two. Now, we use, to figure out the mass of what they're orbiting, we use something called Kepler's third law. We're going to cover that in another week or so, so I'm not going to go into a whole lot of detail about that. In fact, normally in lab, we actually have you take this data and actually measure the mass of that black hole right there. So by looking at the speeds of these, how long they take to go around, that tells us the mass of what's in the middle. If you think about it, if the more mass I've got, the more it's going to sling that star around as it comes around. So these are the orbits of the closest stars. We'll let that run for just a little bit. So the stars closest to the Milky Way, to the center of the Milky Way. So the center of the Milky Way is right there in the plus mark. And these are the stars that are orbiting it. Now it takes, a quarter of a billion years for the Earth, for our sun, to go around the Milky Way. But these are orbiting just in the case of a few dozen years or so, because they're so close. The galactic center is kind of a fascinating place to get down there and explore. All right. So let's get into some of the weirdness. And if you look at your class notes, you'll notice that we're basically done with the class notes. So at this point, you don't need to be taking any notes other than just, things that you're interested in, things like that. But this is the part that we kind of just want you to have fun with and kind of expand your mind a little bit. So I was in Syracuse one time at a talk, and Stephen Hawking was presenting. And so this was the slide that he first presented as the title of his talk: The Breakdown of Physics in the Region of a Space-Time Singularity. You guys know that a singularity is a black hole. That's the point in the middle of the black hole where all the mass is contained. His next slide that he put up looked like this: The Breakdown of Physicists in the Region of a Space-Time Singularity, because things get crazy as we start approaching a black hole. Time slows down, things like that. So we're going to see what's going on with this, and things are going to get a little bit strange. So I've got to build up to that. So we're going to talk about this idea of space-time and what space-time is. So let's just say that you had a regular graph. This is the y-axis, this is the x-axis. And suppose I wanted to know, what is the distance between these 2 points? This point x1, y1, and this point x2, y2. Well, you might say, we'll just stick a ruler down there and measure it, Kilo. Well, unfortunately, we don't have a scale here, so we don't know how big these things are. So the way we can do that is using the Pythagorean theorem. And how many of you remember the Pythagorean theorem from high school? Yeah, most of the time I find that's the only thing that people remember from math in high school, is the Pythagorean theorem. So Pythagorean theorem is c squared equals a squared plus b squared. So if this distance is c, then we'll call that d. This distance for this side of the triangle, would you agree that if this is x1, y1, and this is x2, y2, that's going to be x2 minus x1. That's going to be the distance here. Can you see that? And this distance here, remember this is x1, y1, this is x2, y2. The distance here is going to be y2 minus y1. This little symbol here, this delta, you should remember that from the Doppler effect. This means change in. So this is the change in y, this is the change in x. So we can just think of this as the distance in x, the distance in y. So Pythagorean theorem says d squared equals a squared, or in this case delta x squared, plus b squared, which in this case is delta y squared. So that's how we find the distance between 2 points in space. Well, let's talk about space and time then. So for now, just to keep it simple, we're only going to look at one space axis here, x. Now we could have y, we could have z, but now you got to draw in 4 dimensions, and that's something I'm not real good at. So, but perpendicular to space is time. All right, so let's say that you're sitting here at the origin, and let's say you don't move anywhere. So you're just letting time pass. How are you going to move on this graph? Pause the video, think about it. All right, well, if I'm sitting here at the origin and I'm not moving, then I'm not moving through space, but I can't stop myself from moving through time. So I just move straight up, just like this. And I'll continually move straight up, just straight without moving in the x direction at all. All right, so now if I'm moving in both space and time, I'm still going up in time, but now I'm starting to move in distance. Now I can't go from here to here because that would just be teleporting. I'd be moving in instantaneous, no time having passed whatsoever. So since I can't teleport, then I move at this angle. And the greater the slope, the greater the distance from this t-axis, then the faster I must be going. So if I'm just barely moving, then my line might be right here. On the other hand, if I'm going really fast, my line might be over here. You see how that works? So that slope there, the slope of the line is giving me the velocity. The fastest I can possibly go is the speed of light. So if I choose my units carefully, basically I just need to scale this in light seconds and do this in seconds. So light seconds is the distance light travels in 1 second. Makes sense. So then this angle will be a 45-degree angle. So this would represent the speed of light. Now, since I can't travel faster than the speed of light, I can't exist in this part of space-time. This area over here, I would have to travel faster than light. Do you see that? So if somebody's sitting over here, we're not going to be able to interact until our light cones intersect at that point. So in this region, though, I can reach anything in this region without violating the laws of physics because I won't be traveling faster than light. So, if I decide to go really slow, I might end up over here. If I decide to go really, really fast, I might end over here. We call this the time-like region because I'm moving more in time than I am in space. We call this the space-like region because I'm moving more in space than I am with time. And the key thing to remember here is that space-like regions are illegal. You can't get there. There's no way to get there without violating the laws of physics. Time-like regions, though, do not violate the laws of physics. And this is going to be important when we talk about time travel. So keep this in mind. As long as I stay inside this part, this little cone here, this triangle, that is going to be legal. It's not going to violate the laws of physics. So if I'm going to do time travel, I have to be in the time-like part of the curve. So keep that in mind. So now let's imagine 2 dimensions. So here I've got the x-axis, here I've got the y-axis. So keep that same 45-degree angle, and you see that I can reach anything inside this cone. I can go this way, I can go this way, or whatever. We call this a light cone because it's defined by where light can travel. So by the edges of the speed of light. So this time-like region is everything inside this light cone. Now another thing to keep in mind is that the time axis is always perpendicular to space. So if I've got 2 of them, it's always going to be this way, right? So if I'm not moving, I'm just going to move straight up along this. Okay. So what we're doing is we're building concepts that we're going to use that's going to help us understand black holes and warp drive and time travel. So as I said, I can travel at any speed as long as I stay inside the light cone. The closer I get to this light edge here, this is the speed that light travels. We call this the light-like region, but whatever, the surface of the cone. The closer I get, the faster I'm going to have to burn my engines to get there. But there's no way that I can leave that light cone. All right, so some funky things start to happen when I'm traveling at speed. Let's say that I'm moving at speed, and we've gone back down to 2 dimensions here to make it easy. And let's suppose that I send a light pulse every second. So beep, 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 beep. So I'm sending that light pulse out. But let's suppose that there's another observer who, maybe you are sitting on the Earth and you're not moving at all. Well, if you're not moving at all, then through space, then you're going to just move through time just like this. But when you receive each one of these pulses, the distance between the pulses is greater than 1 second. Take a look at that. So each of these pulses is 1 second apart, and as near as I could draw them anyway. So each one of these pulses is 1 second, but this distance here is longer than this distance. And that difference will be greater the faster that you're going. So this is called time dilation. Time is actually traveling more slowly for you when you're moving than it does when you're standing still. And so one way that I could use this, if you ever heard of the twin paradox. So let's say I've got these twins and I put one in a rocket ship and I send him off into space moving really, really fast. And maybe he spends a year there. When he comes back, 50 years have passed on Earth, even though only 1 year has passed for him. So this is the first form of time travel. You can move into the future by moving at a very quick pace. If you're moving at a high velocity, then time is passing more slowly for you than for people who are left back at Earth. And so by the time you get back, even though you've only spent a year, you've traveled 50 or 100 years into the future doing that. This is also going to be important when we start building our time machine. But this is the kind of the first step towards that. So pause the video if you need to, think about it, see if that kind of makes sense. If you see why you'd be moving into the future, because time is moving more slowly for you. All right, so observers don't agree on the amount of time passed. You say a year has passed. People on Earth say, no, you're crazy. 50 years have passed. And as it turns out, and I'm not going to prove this because it's a little bit harder, but it turns out that they don't agree on length either. When you're traveling at very high velocities, your length actually gets shortened. It's called length contraction. So time dilation means time stretches, but length contracts. And so you're actually shorter in the direction that you're moving. The person on Earth says, no, you're not. That's crazy, So they don't agree on time and they don't agree on space. But there is one distance that they do agree on. If instead of writing my distance, this would be using the Pythagorean theorem if we forget the time part for a minute. So delta D, remember we had that before, we're going to use an S now because we're going to be using space-time, is the change in x squared plus the change in y squared. And of course, if I do it in 3 dimensions, then it's going to be plus the change in z squared. And so that would allow me to move in any direction. But if I add this time component here, so it's negative delta t squared plus delta x squared plus delta y squared plus delta z squared. If the person on Earth calculates that and the person in the spacecraft, the moving spacecraft calculates that, they get exactly the same number. So they don't agree on the time passed, they don't agree on the length passed, but they do agree on the combination of those two with that. And so this is proof that Einstein discovered that shows that space and time are two parts of the same thing that we call space-time. So space and time cannot be separated. You get all kinds of weird results, but when we put them together, everything is consistent and everybody agrees on everything. Now, what makes time unique is this negative sign here. All the rest of the dimensions have a positive sign. So if I were moving in a fourth spatial dimension, I might have a plus delta w squared or something like this. Time is not a space dimension. It's different. That negative sign is what's making it different. So something about this negative is what's pushing you through space-time. This is what's making it so that you can't stop yourself from moving through time, even though you can stop yourself from moving through space. Exactly what, we don't know, but this is one of the more interesting things in studying, figuring out how time itself actually works. So what we're talking about here is we call flat space-time, which means there's no gravity, no mass, no energy present. Remember that mass and energy are two forms of the same thing. Remember, E equals mc squared. That basically just says energy is mass, mass is energy. So we'll call it mass energy for that. This is Einstein's equation. And this basically is all of general relativity in one equation. And it's a little more complicated than it looks because these aren't variables, they're tensors, which are, like a matrix of 16 different equations or so. But what this says, T is mass energy, G is space-time. So mass energy tells space-time how to curve. And we're going to talk about that in a little bit. And then space-time tells mass how to move. Well, let's look at that. Let's imagine that space-time is a rubber sheet. And now I've got a ball that represents T, that represents my mass energy. So that ball stretches that rubber sheet. So the ball is telling space-time how to curve. On the other hand, if I have another ball and I roll it this way, it's going to roll down until finally it impacts the ball down here. So space-time is telling matter how to move. So when we're doing a graph like this, thing I want you to think about is the x and y axis here is the sheet. So this is, let's call this x and maybe this is y. And then perpendicular to that is time. So this ball, as it moves through time, just moves straight up, but the whole sheet moves with it, okay, as it's moving through time. Let's look at that a little more carefully. So looking at it from the edge, because you guys know I can't draw in 3D, here's my light cone. So and here's where that ball is. The ball is sitting down here in the bottom. It's curving space-time like this. If I'm sitting out here, then my light cone is slightly tilted because remember, it has to stay at a right angle to the surface here. So it's slightly tilted. So Earth, because we're going to assume that it's not moving, our planet is just moving through space-time straight up. If I just sit here and do nothing, I'm actually tilted very slightly towards the Earth. And so eventually I'm going to fall and I'm going to hit the Earth. Let's look at something a little closer here. As we get closer to the Earth, do you see that the tilt is greater? And so just by existing, because I can't stop myself from moving through space-time, I can't stop myself from moving through time in particular, I move along this axis and you see that I'm eventually going to hit the Earth. So let's draw on the screen here, get my tablet. So Earth is going to move, I'm hitting a button, sorry. Earth is going to move straight up like this. You are going to move this way. And you see that eventually you're going to crash into the Earth. From our perspective, it feels like gravity. But gravity is not actually a force. Gravity is actually just the curvature of space-time. And then just your moving through time causes you to intersect the Earth. You get closer and closer and closer. So the effect is the same as, Newton's gravity dropping an apple and all that other sort of stuff. But the reason why you move is because Earth has curved that space-time. And as I get closer to the Earth, that space-time, that tilt of my light cone gets even greater, and so I fall even faster. I move even quicker to hitting the Earth like this. Now, I could, let's say I'm out here, I could burn my engines, and then I'd be moving this way, and eventually I could escape. So this is why you need to burn your engines to get away from the Earth. On the other hand, if I'm sitting out here in space, I could burn my engines this way, and now I'm diving down towards the Earth because I'm actually going to hit it faster. All right, so this is an important result. Let's stop and think about that then. So if I'm way out here, I don't have to burn my engines very fast, and I will be able to get away from the planet that's here. On the other hand, if I'm over here, I've got to burn crazy fast before I can get there. Well, this curvature of space-time we can actually see, because as light comes in to the sheet, it gets bent around like this. If the light's going fast enough or the gravity's small enough, then it can actually come in. Let's see if I can draw this. Get bent, and then as it moves out, it goes straight, whereas some light from over here gets bent this way and then comes out straight. So you see that what happens then is I get two different images of the same object. And that, of course, is also going to go this way and this way, because remember, gravity is going to be in the sphere. Well, we actually have seen that. And at first, this kind of looks like an alien spacecraft sitting out there. But this is called Einstein's cross, and it looks like there is 4 stars surrounding this central star here. And I'm going to zoom in on it a little bit. Looks like this. So the center star is really a galaxy. And then behind it is a quasar. These are ultra bright. Turns out they're going to be made from supermassive black holes as well, but they're out closer to the edge of the universe. We'll talk about those later on this semester. So the light from the quasar is behind the galaxy. The gravity is bending the light this way and this way, so I get 2 images from it. And then, of course, it's also bending this way, so I get images here. And what made us realize that this was going on was that these quasars change in brightness fairly quickly, but the change was exactly the same in all 4 of these stars. And it's not possible for them to be that synchronized and to all change in the same way. We realized that that had to be the same object. And so this is a proof of that what we're talking about is real. Space-time is being curved by the mass of that galaxy. All right, so let's stop and do a quick review. So space and time are 2 parts of the same thing. You can't separate them. We've got to have these light cones, and then the light cone stays perpendicular, that shows time, stays perpendicular to space. If space is flat, then it's going to act kind of how we're used to thinking. But mass and energy cause space-time to curve, and so that's going to make your light cone tilt. When the light cone is tilted, then you can't stop yourself from moving through time. So if you do nothing, you're going to smash into the Earth. And the light is affected by curved space-time just like matter. All of these pieces we're going to build together when we start talking about black holes and time travel. Okay? So pause the video, think about that for a minute, then when you're ready, let's move on to the next stage. All right, now, don't be frightened by the math, but this is called the Schwarzschild metric. So this is nothing more than that Pythagorean theorem that we were talking about. So we had delta S is minus t squared plus, and I'm doing this in spherical coordinates because we're talking about a ball. So there's this, instead of x, we've got r, but think of it as being the same way. But then we've got these components in front of it, this 1 minus 2m over r and 1 divided by 1 minus 2m over r. This is the amount that space is curved. So if these things were not here, if this were just a 1 in front of this and a 1 in front of this, then we've got flat space-time. That means there's no matter, there's no planets, there's no black holes, there's nothing like that. But this case shows when I've got an actual object there in the middle. And all of these things, all these metrics are solutions to Einstein's equation. So they don't violate that g equals 8 pi t. They don't violate the laws of physics. So anything that solves that equation, and there are lots of solutions to it, that's going to be legal in our universe. Well, let's look at what's happening here. So mass is curving space-time depending upon its distance. But look, something weird is going on. When we're at a distance equal to 2m, and we're not going to worry too much about the units, but when r equals 2m, this is 1. 1 minus 1 is just 0, which means that time actually stops when you get to that point. Also, 1 divided by 0, well, that's infinity, or undefined, really. And so that means that something really strange is going on at this distance of r equals 2m. So time stops, and it works out that this actually is the mathematical description of a black hole. And so everything that I'm going to be showing you from here on out comes from this mathematical description of a Schwarzschild black hole from that. So this r equals 2m is going to be the event horizon. Okay, so let's look at what's happening here. So remember that I'm moving in time this way, so going straight up. So this circle here, this disk then forms a cylinder as it moves up. That's the event horizon. So anything that passes inside that is not going to come out. This line in the middle is the singularity itself. Now you see out here, this is my light cone. So if I do nothing, I'm just going to go straight up and I'm just going to look at that crazy black hole out there and go, wow, man. On the other hand, if I start moving towards it, the closer I get to the black hole, the more curved space-time. Remember, it curves this way because of the black hole. So the more curved space-time is going to be. And so if I do nothing when I'm here at point P, now, lost my mouse, there we go. If I do nothing at point P, then just by existing, I travel through the center of the light cone, and you see that eventually I'm going to hit that black hole. So the black hole has me, and it's dragging me in. That tilt gets greater and greater and greater. Once I cross the event horizon, right here at the event horizon, I would have to travel at the speed of light to escape. Remember that I can't leave my light cone. And so there's no way at this point for me to escape because I can't travel faster than light. Here at point P, I can still escape, but I've got to really burn my engines hard. I've got to be moving close to the speed of light in order to get out. But once I cross that point of no return, there is no escape. Eventually, if I do nothing, then I'm going to hit the singularity and I'm going to be crushed to size 0. On the other hand, if I burn my engines, I can at least delay it for a long time, depending on how fast I can go. If I could somehow travel at the speed of light, then I could just sit here and hover on the edge forever, but unfortunately nothing can reach the speed of light. So at some point, you're toast. You're going to be compressed to size 0. So take a look at that. These light cones are showing us why you can't escape. Because remember, I can only stay in the time-like region. I can't come out into the space-like region. Well, once that cone is tilted, because space is curved underneath it, so if we were drawing it right here, it would be, something like this, maybe. Okay, so you see that light cone has to stay perpendicular to the surface. Okay. So once inside the event horizon, you're toast. You are going to be crushed. Your fate is sealed at that point. It's just a matter of when is it going to happen. So this is showing us the inside of the black hole, but remember that crossing here, it's not something physical. So once you cross that event horizon, you're perfectly fine, especially if it's a supermassive black hole. You're not going to get stretched or anything like that. You just walk right in and it's no problem. The difference is you ain't getting out. So this line right here represents the singularity as it moves through time. So it starts here and then time is moving this way. This is my light cone, and if I do nothing, I'm going to end up this way. Okay. So let's look at the same idea of light pulses that we talked about when the object was moving really fast. So let's say that the spacecraft is coming down and it's going to dive into the black hole, and he's sending out a pulse of light every second. So that light, and that's what these light cones are showing you here, that light travels at the speed of light, so it's always going to be on the edge of one of these light cones. But as I get closer and closer to the black hole, my light cone starts to tilt. So when I get here at the edge of the black hole, as soon as I cross that event horizon, the light never reaches Earth. It just stays there. It just seems like it's stopped. And so this is actually a characteristic of black holes. As things start falling towards the black hole, it looks like time slows down. So let's look at this right here. Let's say I've got two observers here. And so one is my dude C is going into the black hole. He's falling in this way. And then I've got my other observer here at Earth or in another spacecraft sitting outside who's kind of watching this crazy guy fall down into the black hole. So remember, the spacing between these light pulses is 1 per second. But when he's out here, the time between here and here is actually greater than 1 second. So from the point of view of observer A, C looks like time is slowing down for him the closer he gets to the black hole. And you see that as he gets closer, the space between his pulses gets even greater and greater. So let's imagine that each one of those pulses is the tick of a clock. At start, he's just 1 per second, but then it takes longer and longer and longer for a second to go by. So when we're talking over radio or over a video feed or something like that, the dude in the spacecraft looks like he's going slower and slower. From his point of view, he's doing fine. You know, there's no difference. But once the spacecraft gets to the event horizon, that light pulse never leaves. And so the spacing, as he approaches it, the space between them gets long, between light pulses at Earth, gets longer and longer and longer. So from the point of view of this observer A, as the guy dives in to the black hole, time moves slower and slower and slower. And then once he hits the event horizon, time stops. And so his image is frozen there on the event horizon forever. So you can kind of envision these as being, you know, kind of the ultimate gravestone, because you're dead. You've been compressed to size 0 in a pretty painful way once you finally hit the singularity here. But your image remains. The last light that you left just before you cross that event horizon stays there forever. And so, you know, you can imagine people, you know, wanting to commit suicide or whatever and leave a memorial to themselves. They dive in and now their image of their ship is left suspended for all eternity right outside that black hole. So let's go with that. So let's tell you a little tale here. Romeo and Juliet, a tragic tale of suicide and spaceflight. All right, so let's suppose that Juliet has broken up with Romeo and he's so despondent that he's going to kill himself. So he decides, I'm going to get in a spaceship and I'm going to dive into that black hole, and that way you're going to have to look at my image and see what you missed forever, bitch. Right? So he gets in a spaceship and he starts diving in. What he doesn't realize is that Juliet actually does love him. And so she's left a note in his spacecraft. So he gets to right here and he reads that note and it says, Romeo, don't kill yourself. I love you. Come and let's be together. And he says, hell yeah. And so he burns his engines hell-bent for leather, and Juliet burns her engines, and they meet up here and they live happily ever after. Boring. Take 2. So let's suppose, same situation, he dives into the black hole, but he doesn't read the note until he crosses the event horizon here. Well, he's not coming back at this point. Juliet knows that because she can see that his image's time has slowed down and she sees that it's stopped. So she starts diving into the black hole as well. Now, as she gets closer and closer to the black hole, she's going to start to intercept some of those light pulses that he was sending out. So from her point of view, he's stopped, but as she gets closer, time starts to speed back up for him. so that once she crosses the event horizon, and he, of course, has been burning his engines hellbent for leather, they're able to meet right here. They transfer into each other's spacecraft, and they stay together so that they fall together onto the singularity and get crushed into nothingness, and they both die a horrible death. Much better. Take 3. So in this case, Romeo doesn't read the note until much later. So Juliet dives in, but Romeo, even moving at the speed of light, can't avoid hitting that singularity and in time to meet up with Juliet. So the both of them dive in, they get crushed horribly into nothingness, but they never see each other and they never meet. Ha! And that's the best one. Okay, so all of these things coming about, all of these 3 situations then come about because of that light cone tilting from that. But that's what's causing this difference in time dilation. All right, well, this leads us to the idea of warp drive. So Miguel Alcubierre is a Mexican astrophysicist who has invented the very first warp drive. And they call it warp drive because it works exactly like the warp drive from Star Trek. And here's our space-time. This is our rubber sheet. And you see that we've got our traditional bending down here, but notice that I've also got it bending up like this. The spacecraft just sits here in the middle. It never travels relative to this bubble, this warp bubble that it's sitting in. However, because this bubble is pointing up, then if I were to draw a light cone, and I don't know if I can draw it where you can see it on here, but if I were to draw a light cone, that light cone would be pointing forward. Do you see that? And so just by existing, you move forward. And you never leave your light cone. Remember, I have to stay in the time-like region. But because of the way this is peaked up and then peaked down, you move forward and the bubble moves forward because it's falling towards the front part of the bubble from it. So that allows you to move as fast as you want to go. The only thing that's different that changes is, the higher that height of that bubble is, the faster you're going to move. And you can, in fact, move faster than light this way because that bubble just moves along with you. The reason you can move faster than light is because you never, ever leave the time-like region of your light cone. So you don't violate any laws of physics. In fact, you don't even feel any acceleration. So you can be going crazy fast and you're just sitting there floating. You're in free fall from this. So this is the first practical warp drive that we could use. Now there is a problem with this. I need to get this up peak. Well, normal matter always causes space-time to bend downward. So this is negative matter. Now I don't mean antimatter. Antimatter still has positive mass. So it still distorts space-time this way. We need this kind of exotic matter that repels everything rather than attracting it because it distorts space-time this way. Now, we don't see any of that in our universe. However, as we're going to talk about when we start talking about cosmology and the birth of the universe, this stuff had to have existed, or else the universe we have right now would not exist in the form it is right now. So we're almost positive that this negative matter exists because everything we know about astronomy and space-time breaks down if it doesn't exist. The question is, where is it? So finding that negative matter we're going to see is going to be a theme. That's basically your dilithium crystals if you watch Star Trek. But that's what's going to be powering your warp drive. And we're going to see is what's going to be powering your time travel. So another way to travel faster than light. So this is, like I said, warp drive, just like Star Trek warp drive. Another possibility is to use a wormhole. So here I've got 2 black holes that are joined together so that they've got kind of a throat. And then you can pass through this distance very, very quickly. Whereas the alternative to travel between them, you'd have to go through all of space-time like this. So this also allows you to travel effectively faster than light. But your light cone, you never leave your light cone. You're always in the time-like region because you're just falling into a black hole. And so you never see, nobody sees anybody traveling faster than the speed of light, yet you arrive at the blue point faster than light can get there. So again here though, you want this to be a supermassive black hole because otherwise you're going to get stretched into that spaghetti. So the idea of having stargates, probably won't work. On the other hand, you could find a way to connect these 2 supermassive black holes. But for fun, let's suppose that we could figure out a way to make a small localized black hole. So we would have to actually create this. It wouldn't be a naturally forming one. It would have to be one that we would create. But remember, mass and energy are two forms of the same thing. So maybe we could use a lot of energy, concentrate that together, and then somehow create a black hole from that. Let's suppose we could do that. The problem is that the throat here, where these things are connected, it's going to want to collapse onto the singularity. So if we do the calculations on a wormhole, it turns out that we need to line the throat with negative matter to keep that throat open so that you can just dive right straight through and come through the other side. So wormholes also require that exotic negative matter for this to work. Okay? So again, that seems to be the secret, and we know that it has to be there. It's just a matter of where is it? Where can we find this stuff? So wormholes can be easily used for time travel. And I'm going to show you a better picture of this. But it turns out that anytime I have something that travels faster than light, that has the potential of traveling faster than light, I have the potential to also build a time machine. You can't get one without the other. So let's talk about that. So wormholes can be easily used for time travel. So let's put this end of the wormhole in a very fast-moving spacecraft. This end we're going to leave on Earth. Well, you guys know that if you're moving out in a spacecraft, time travels more slowly for you. So let's suppose that my wife and I have built this wormhole, and one end is sitting in my rocket ship that I've got in my backyard, and the other end is sitting in the house. So Sally and I, of course, we're married, so we hold hands, because we're all lovey, and we hold hands through the wormhole, so while I'm on this journey, we can still be touching each other. So I go off in space, and I travel at a significant fraction of the speed of light. And let's say that I'm gone for a year, and we're still holding hands through the wormhole, yada, yada, yada. However, time is passing more slowly for her. And so let's say maybe 10 years have passed on Earth. I come back. When she looks through the black hole, remember, through the wormhole, 10 years have passed for her, but only 1 year has passed for me. So when she looks through the black hole, she sees the world as it was 9 years ago. We have made a time machine. All she needs to do if she wants to go back in time 9 years is just crawl through the wormhole, come back into my ship, and she's in the world of 9 years ago from that. And so we can always find a way to do this. Now, one of the keys to time travel, though, is that, and it turns out you can prove this mathematically, but you cannot travel back in time further than when the time machine itself was built. There's no way to do that without violating the laws of physics. So the reason we haven't seen time travelers appear everywhere is nobody's built a time travel yet. Nobody's built a time machine yet. So the way you can tell that the government has built this secret time machine is when suddenly we start having time travelers appear everywhere, because that will be the earliest that they could ever come back. So you're not going to be able to go back and see the dinosaurs or anything like that. Somewhere we got to build that time machine, and then we can come back to this point, but no further back. So this leads to some paradoxes. Anytime you have a time machine, you might conceivably have some paradoxes. So if you want to look at how to build one of these things, you're looking for the idea of a closed time-like curve. That's code for time machine. Now, if we were to publish an article in, Astrophysical Journal or, one of the research journals called Time Machines, they would reject it. But closed time-like curves is well within Einstein's theory, so you can talk about this. And so this is what we're talking about with a closed time-like curve. If I'm just sitting here and I did nothing, I would pass along this line right here. So you see that if I were just sitting here at Q, I'd just go straight up. So anything that stays inside my light cone is going to be time-like. So it's part of my accessible part of my universe. But let's say that I warp space in such a way that my light cone tilts. So get my camera back here. So if my light cone tilts, I can stay inside that light cone and I'm not violating any laws of physics. And then I could come back at point P, but point P is prior to, in time, than point Q. So I closed the curve, but now I'm earlier in time than when I started. So a closed time-like curve is code for a time machine. Well, this, as I said, brings up some paradoxes. So the idea of causality is that one event causes another event, and that's kind of fundamental to how we think physics works. So if I've got a cup on the table here and it falls off and breaks into a billion pieces, it will always break into pieces after it falls. You'll never find it to break into a million pieces and then fall. You see that? That would violate causality. But time travel allows a violation of causality. And so the classic is the grandfather paradox. So let's start up here. So I'm born and I create a time machine. And I go back into the past, or I find one, because we now know we can't go further back than before the time machine. But I go back into the past and I kill my grandfather before he had any children. Well, if he didn't have any children, then my father wasn't born. If my father wasn't born, then I wasn't born. Well, if I wasn't born, then I didn't make the time machine. If I didn't make the time machine, I can't go back in the past. Well, if I didn't go back in the past, then my grandfather is alive, and so my father is born, and so I'm born. Well, now I can make the time machine. So there's this issue of, well, you've got this paradox, And there's been a number of ways that have been proposed to try to resolve it. One is that you're unable to kill your grandfather, that fate will interfere. So, you pull the gun out and you start to shoot him and your gun jams and he gets away. And so one theory is that you don't actually have any free will, that something will always happen that will prevent you from being able to kill your grandfather and cause this paradox. Another possibility is the many worlds hypothesis. Basically, when this cup falls off the table and breaks into a million pieces, it forms a different universe. So there's a universe where it breaks into a million pieces, there's a universe where it breaks into 1,000,001 pieces, and so on and so on. And so you get this infinitely many universes. So in that kind of thinking, I would go back and kill my grandfather. Nothing happens to me because I have effectively created a new universe in which my grandfather never had any children. I'm just a visitor to that universe, and so it doesn't affect me at all. So that's another way that we can think about it. But if we want to know which is true, we have to know, does free will exist? If there's no free will, then we don't need these separate universes. Everything will happen because it was fated to happen. Then there's no real control over it. So there's an experiment we can do, actually a fairly simple experiment we can do to test this. So let's say that I've got a pool table with a wormhole for the pockets. So we're going to get rid of the whole idea of guns jamming or me suddenly getting cold feet and deciding not to kill my grandfather or whatever. We're just going to totally take the humans out of the equation here. We're just going to talk about pool balls. Well, the movement of pool balls on a pool table is actually pretty easy to solve because, if you take physics, if you take, freshman and sophomore physics, you'd be able to solve this problem yourself. So, you hit the ball and it's going to go in a certain angle depending upon its speed and velocity. So what I want to know is there a way for this ball to come into the wormhole and go back in time in such a way that it can knock itself out before it falls into the hole? Do you see that? So if it can go into the hole and come out, go back in time and keep itself from going into the hole, it can knock itself out from going into the hole. This is effectively the grandfather paradox because if we knock it from going inside the hole, then it wasn't able to go through the hole, and so there was nothing to keep it to knock it out from going into the hole in the first place, and so on and so on and so on. So this then turns out to be something that we can actually solve using fairly straightforward dynamics equations. And when we do that, what we find is there is no solution to the physics that will prevent this ball, once it goes into the wormhole, there is no way to prevent it from going in. There's the ball that will either come out and it'll miss always, or it might hit the ball that's going, the future ball that's going in and crack it or something, but it can't stop it from actually going into the hole. So it has been fated that that ball will go into the hole, and there is nothing that you can do to stop it. There is no solution to physics, which means there's no way to do it in reality to prevent that ball from going in. Free will doesn't exist. So some people, one way that you can kind of think of this, there are a number of different ways that you can knock that ball in, And there's a number of different things that can happen. It could, the ball coming back through time might miss entirely. So the way I think of it is that life is kind of like a sonnet. And if you've had any English, studied Shakespeare sonnets, you know that a sonnet has to have a specific form. It has to have a specific rhyme, a specific meter, a specific number of syllables, that sort of thing. If it doesn't follow that format, it's not a sonnet. Within that format, though, you're free to say anything you want. And so that's kind of what's happening here. There are certain events that are fated, that must happen. There is nothing that you can do to stop it. But how that event happens, how you express yourself within that event, is entirely up to you. That's the limit of your free will, but it's an important kind of free will. Okay? All right, so now that I've blown your minds here, let's summarize this a little bit. With black holes, I've got to have the smallest possible black hole is 3 solar masses. I've got to have more than 3 solar masses in one place. So this is greater than 3 solar masses is what that means. To find the size of the event horizon, you just take the mass in solar masses and multiply by 3 kilometers. That's it. The singularity is where the actual mass is contained. That's that size 0 bit. The time slows as we approach that. And so that's what produces that event horizon. And as I hit to the event horizon, then time basically stops. Nothing inside the event horizon can ever come out. When we're talking about warp drive, no object in any of these kind of warp drive things exceeds the speed of light, because that puts us in the space-like region, and that's illegal. I can't do that. That breaks the laws of physics. However, I can cheat. I can curve space-time itself so that I end up arriving someplace before light can get there. And all forms of warp drive, time travel, and everything else seem to require this negative matter. It seems to be that no matter what kind of system you come up with, you're going to need the negative matter to make it work. So the negative matter is the key to faster than light travel and time travel. We know it exists. It has to exist for the universe to look the way it does now. We just can't find it. So that's one of the things that would answer a lot of questions if we could find this negative matter. Okay, that's it. I hope you had fun with this. You might watch the video a couple of times, if things kind of went over your head a little too fast, because hopefully I've made your mind explode from all this, because that's part of the fun of it. But just remember that only the things that are on the practice or on the class notes are things you're responsible for. The practice worksheet is actually quite simple. You shouldn't have any trouble with that at all, but if you do, as always, get in touch with me. And if you do need to get in touch with me, here's live help hours. I hope you're all taking advantage of that. With an online-only class, you really need that interaction. Working by yourself, I've actually done some research that working by yourself just makes it 10 or 20 times harder than either working with me or getting a study group or something like that. So here's when I'm available. Sally's available on Tuesday, Thursday, and Friday, and then Andrea is available in the afternoons. Okay, so that's it for black holes and time travel and warp drive and all this kind of stuff. We'll be working with the idea of black holes later when we start talking about quasars and the supermassive black hole at the center of the galaxy that we'll be studying in some detail when we talk about galaxies. But I hope you had fun. Most of this was just intended to, kind of expand your mind a little bit with that. But maybe you'll start looking at some of the science fiction movies that are out there a little bit differently and say, hey, that could actually work. We'll see you next time.